In this lesson, we're going to tackle differential equations. I'm really excited to teach this lesson to you because not only is it one of the most important applications of calculus, you'll take entire classes on this if you go on in your math career. But it's also differential equations is the only math class I've ever had to take more than once. So as you can imagine, it gets pretty challenging. But actually, it's something you're already familiar with. So this is our very first differential equation that we're going to consider as a differential equation here. It says dy dx is equal to cosine of x. So all it really is an equation relating variables and their derivatives. And this is a very simple one that we're going to consider to start. So we're asked to find this equation's general solution. And another way of asking that question is, for what equations is our differential equation true? That S there will be important to add in. So one way we might figure this one out, this is really, it's like what function has a derivative cosine of x, right? So I might be like, okay, the integral of cosine of x with respect to x is equal to sine of x plus c, right? And that's it. That's my general solution. So it's actually, these are equations you've already known how to solve. Now, sometimes these can be harder or even impossible to solve, right? And here are some examples of harder differential equations down here. All of these, notice, have second derivatives in them. And we couldn't just integrate to solve these necessarily, right? So one way that we tackled these is by what's called a slope field. So what this is a graph of all of our solutions, essentially. And watch what I get if I take a point and follow the slopes. So I just started at the origin and followed my little tick marks. And notice I get that sine wave that I would expect. And notice if I pick a different point, I get that same wave just shifted up. And that represents, of course, our plus c, right? So this is a graph of all of the equations whose derivative is cosine of x. And sometimes differential equations problems are as easy as just interpreting these. So we're given a slope field, and we're given this point 0, 6 as an initial condition. That means we want whatever solution passes through that point. And the way I find that is I just find that tick mark at 0, 6, and I kind of follow the curves. And you don't have to be super precise. And notice at this point I'm guessing because I can see that there's an asymptote there. Let's do one more example. Let's do the point 0, 1 this time as our initial condition. I'm going to have you pause right now and do this one on your own. We'll use green for this second example. So I'm going to find my point 0, 1 is here. And then I just follow my slope field. Again, I don't have to be super precise, but often we're just asked to sketch those solutions. So that's a very easy differential equation problem. What that means, right, is if I took this equation that I don't know, my differential equation, and solved it and plugged in that point, I would get this curve. And we're going to do an example of that on the back of the notes here. Okay, so now let's say I gave you a harder differential equation and asked you to start to solve it, and you weren't sure how. One way you might start to investigate this problem is by drawing this slope field. And the way you do that, so here I have my derivative. I'm just going to start to plug in points. We're going to zoom way in here so we can see what we're doing. You may want to make your notes off to the side. So let's pick the point. We'll use 1, 1 to start, nice easy point, right? And I'm plugging it into the derivative, right? So it's negative x over 2y. That means I get negative 1 over 2. And you should be able to do these in your head, I think. Let's pick another point. So 0, 1, that means I get 0 over 2. And then let's see, 2, 1, that means I get negative 2 over 2, which is equal to 1, negative 1, I should say. And let's do a point over here. So here I get 1 over 2. And let's do this point 2, 0. So here I get negative 2 over 0. Uh-oh. Here I get negative 1 over 0. Uh-oh, right? So those points are not going to get a point. We'll do just a couple more. So here we're going to get 0 over 4. So still 0. Here we're going to get, let's see, 1 comma 2 is my point, so we'll get negative 1 over 4. Here we will get negative 2 over 4 is negative 1 half. And we can probably start to see the pattern, right? So here I'd probably get 1/4. Here I would probably get 1 half. So then what I can do is I can just sketch little line segments with roughly the correct slope. So 1 half should be, less than 45 degrees, but not horizontal. We're going uphill is positive. Let me go a little bit flatter. It should be pretty flat, right? 1/4 is going to be even flatter. 0 obviously going to be horizontal. Negative 1/4 should be about as flat as 1/4, but going the other way, going down. And here we have a negative 1, so steeper still. Here we have another negative 1 half, so there should be parallel, positive 1 half, and we start to see the shape, right? So that's my slope field. And I could do, if I wanted, all of these points and get a full slope field that would start to look like something like this. Okay, so you don't often have to graph these by hand, but it's important to know where they come from. And it's just plugging in points into the derivative. And make sure you make yourself this note since we didn't really show any work here. We're going to skip B for now. B is very similar to what we did above, and it's not a very nice graph for it. All right, on the back, rather than just trying to sketch these guys, we're going to actually start to solve them. And we're going to do so using a technique called separation of variables we're only going to study in this class separable differential equations. Where they get really hard is where you can't separate them. And you'll see what I mean by separate here in a second. The first thing I'm going to do is just write the equation. So I'm given that the slope of the curve is blah, blah, blah. So that means, and it's good to use this notation here, you'll see why in a second, dy dx is equal to blah, blah, blah. And then I'm going to separate my variables. So what that means is I'm going to divide the right-hand side and the left-hand side by y, because whatever I do to one side, I have to do to the other. And also, here's where we get kind of weird, I'm going to multiply both sides by dx. And why did I do that? Well, boom, and boom, right? And what is left, I'm going to write it this way. Hopefully you'll understand why. 1 over y dy is equal to 3x squared dx. And once I've separated now my variables, so notice y dy, x dx, well now I can integrate both sides. So once I integrate both sides, then I'm just using my rules for my cheat sheet, and I get the log of y is equal to x to the third plus c. And you may be thinking, like, why did I write plus c on the right but not on the left? And the answer to that is it does not matter. You can write it on either side. You can write it on both sides, actually. That would also be correct. It's really up to you. That would be making more work for yourself. Now, here, we're basically done, but we want to isolate y. To isolate y, we're going to use a trick from pre-calc. I'm going to raise both sides to the power of e, and that's to cancel out the natural log, right? So what's left over then is y equals e to the x to the third plus c. And in this situation, ask me in real life why, but it is a fair move to kind of pull out the c and leave it as c x to the third. Okay, so there is my solution. This, by the way, is called the general solution. So it's a solution to our differential equation with the c in it. It would give us a big slope field like we saw on the front. My particular solution, well, I have this point 0, 8 that I didn't use at all. So 0, 8 would give me 8 equals c e to the 0. That's really 8 is equal to 1 times c. C obviously then is 8. So then my final equation would be y equals 8e x to the third. And this is what is called my particular solution. So it uses the initial condition. Another thing that we can do here is we can do linear approximations. Now notice this is a delta math problem, and this is something that we covered already at this point in the course. So you have notes on this. So feel free to stop watching now, or feel free to skip to the end and just copy down this example. or continue watching in real time if you prefer. So remember what we're trying to do here is we're trying to do an equation like this. We'll do a y minus y1. And in this case, we are given the point, right? So we have the point 2 comma 630. Only this time, my slope is given by a differential equation. So I know that dA dt is equal to negative 190 a, right? And here is the only trick to this that is somewhat new. We are not plugging in the x value here. We are plugging in the y value in this case. So this is my slope, right? That's going to give me negative 7. And then I just plug everything into my equation. So that gives me my tangent line. And then I would, of course, plug in t equals 1.8 and solve. And the result you should get, in case you want to do it and check your work, is 631.4. Okay, so notice, given a differential equation, if we know a point, we can also make a guess at another point on the curve.